Okay, so parallel circuit. This type of arrangement class is when we join the component to a common point. Okay? Let's say, for example, from one end of the resistor, you will connect it to a common point, the same with the another end. Okay? In this kind of arrangement, so we will be having many paths for our current, unlike in the series where the path is only one. Okay, so let's say for example you have here a one resistor. Okay, so like we've said, we will join it to a common point. So the other resistor, okay, as you can see, we will connect it from here. So the common point here is this one and this one. So the leg of the one resistor is connected to the same or to the other leg of the resistor. So let's say this is our common point. Okay, so as you can see, you have connected it here at the common point. So this is again our common point. Okay, common point there. Let's say the other one at the top, this is our common point. So as you can see, the other leg of the resistor is connected there also at the common point. Now let's say we have added another resistor there. So we will also add, or we will also connect the other end to that common point, which will result to a parallel. As you can see, the resistors are connected in parallel, and from that we have produced paths for current. Okay, what are those paths? Here, so let's say your current is coming in here, so there will be road, or there will be path going here, while there will be current also which will go forward. So as they go there, so meron din ditong pupunta, and something is going forward also, and meron ding pupunta dito. Okay, so as you can see, in this case, okay, we have produced, or we have generated many paths for the current to flow. Now when it comes, class, to parallel connection, what will happen to the values of resistances? Now, as you can see, we have here the formula where your total resistance, by the way, I have represented here the total resistance as our R sub P. Your P there represents your parallel. So when you connect your resistances in parallel, the total will be R sub P, okay? But you can also use the R sub T. As you can see, we have also taken the sum, but take note, sum of the reciprocal, okay, sum of the reciprocal, but also after getting the sum of the reciprocal, we have taken also the reciprocal of the total resistance. So therefore, class, in this case, for us to get the total resistance of parallel, so we will simply add here the resistances. Okay, R sub 1, you have here 1 over R sub 2, plus 1 over R sub 3 raised to negative 1, or that is, which means reciprocal. Okay? Or you can simply have it, instead of 1 over R sub 1, you can have it R sub 1 raised to negative 1 plus R sub 2 negative 1 plus R sub 3 negative 1, and then you raise it to negative 1 instead of having that reciprocal thing. Okay? Class, like you said, our connection here is not limited to 3 resistances. In this case only, we have illustrated 3 resistors, but of course you can add more in parallel. Okay, so when you do that, so you just add the reciprocal of it and then get the reciprocal to get the total what do you call this, value of the resistance there. Now here, in resistance, okay, if you go back earlier, this one, if you go back here, the expression, the expression here, which is 1 over r sub 1, is what quantity? If you could recall, the reciprocal of a resistance is what we call conductance. Okay? So therefore, this 1 over r sub 1 can be represented as G sub 1. The same with other reciprocals there. We have G sub 2 and we have G sub 3. Okay? So therefore, class, if for example in the problem, the given is not resistance but rather conductance, so you can still be able to solve for the total resistance, which is connected in parallel. Okay? By simply adding the conductances. Okay? Adding the conductances and then getting its reciprocal. Kasi from here, as you can see, the R sub P will be taken as G sub 1 plus G sub 2 plus G sub 3 and then raised to negative 1. Okay? So that is the sum of the conductances is getting the reciprocal of the conductances, you'll have that total resistance in parallel. So therefore, class, if in the problem you are asked to solve for the total conductance of the circuit, so you simply add their conductances. Okay? Now, let's say that we have supplied source to our parallel combination. Okay? So we have here a voltage, and our parallel combination, of course, once there's a voltage, there will be current flowing. And as you can see, it is coming right here, this one. Okay? Now, as it goes here, this is what we call the node. Okay? Node is because there's different paths. Now, as it goes here to the node, so from the total current, so the current will be distributed. Okay? Some of the currents will go here to the R sub 1, other current will go here through the R sub 2, and some current will go here. And at some point, okay, they will go back here, or they will meet again to another node, and what will go out here is the same value as I. So whatever value here entered at this node, the same will go out here. Okay? So as you can see, or as you can observe, class, in this case, like we have said, there are different currents in each resistors. Okay? Unlike in the series circuit that whatever current R sub 1 has, the same goes to R sub 2 and R sub 3. In this case, class, in parallel, different values, especially if your resistances are different, having different values, class, they will also have different current. Okay? So from this, class, we can conclude that your total I is the sum of the current in each branch, or the current flowing in R sub 1 and the current flowing in your R sub 2 and R sub 3. You just sum it up and you'll get the total current. Okay? Now, how about for the voltage? If in the series, the voltage is distributed, in here, class, it is the same. Take note, it is the same. Why is it the same? What's the explanation behind that? Now, if we consider, class, at this point, okay, at this point, still the voltage is equal to the total voltage, or the applied voltage. Now, since this is just a wire extended, okay, and there's no resistance, but actually there's a resistance, small resistance, because of the wire. Okay, so at this point, still the same, right? Because it's just a wire that is being extended. Now, let us go here. At this point, class, okay, and at this point, still the voltage is equal to your V. Can you follow? It's because, class, we just extended the wire. Can you follow? We just extend the point. Now, the question is, what is the voltage across your V sub 1? The question is, from here up to here. So what is the V sub 1 or the voltage across it? Now the answer there is, it is equal to V or your applied voltage. Why again? It's because, as you can see, this part right here is somewhat, it's just common point. Can you follow? We have just extended the wire, but they are just connected in one point. Somewhat, you just like this, like that. Can you follow? They are just in one point, which means that the voltage supplying in your here is just the same, supplying in each branches. Now, the current class is inversely proportional to its resistance. Okay? What does it mean? It means that if your current, the value of it is high, okay, what will happen to your current? Your current will be lesser. Okay? Which means, class, that if for example, let's say your R sub 1 is 1 ohm and your R sub 2 is, let's say, 2 ohms. And let's say your R sub 3 is 3 ohms. Okay? Now, which resistor does have the highest value of resistance? So obviously it is the R sub 3. Okay? So from this, what can you expect in the case of the current? We can expect, class, that here in R sub 3, the I sub 3 will have the lowest value of current. Okay? Comparing to I sub 2 and I sub 1, I sub 1 will have the highest value compared to this 3. Okay? And when you sum this up, it will be equal to I. Can you follow, class? Just like in the series, if your resistance is high, okay, the voltage drop there will be high also. But in this case, they are inversely proportional. So if your resistance is high, your current there is small. Okay? Now, the total resistance of the circuit, class, is always less than the smallest of resistances. What does it mean? If you could recall there in our series, the total series resistance is higher than the highest individual resistance, right? Now, in this case, it is lesser than the smallest resistance. Which means if you get, or if you compute for the total resistance of these 3 resistors, okay, this R sub 1, so using the formula, R sub 1, negative 1, R sub 2, negative 1, plus R sub 3, negative 1, raised to negative 1. Okay, kindly calculate, class. Substitute natin na R sub 1 is 1, plus your R sub 2 is 2, and your R sub 3 is 3. We have negative 1 and raised to negative 1. Okay, let us calculate. Okay, so using your calculator, so we have 1 raised to negative 1. Are you following there in your calculator so that you can see it? 2 raised to negative 1, plus you have 3 raised to negative 1, and then the quantity will be raised to negative 1 again. So the value is 0.545. Okay, 0.545. Okay, 0.545, and the unit, of course, is ohms. Now, what can you observe, class? The value is smaller compared to the smallest value given. Oh, from the 3, R sub 1, R sub 2, and R sub 3, which has the smallest value? Obviously, it's the R sub 1. It only has 1 ohm. Now, compare the value to the total resistance. As you can see, the total resistance is smaller, right? So, therefore, class, you have to expect you have to expect there that when you connect resistances in parallel, it will result to a smaller value of resistance. Can you follow? That's why, class, when in real world, if you want to produce high current, or you want to have high current flowing in your conductor, then you should connect resistances in parallel so that the current will get high. Can you follow? Okay. Now, if n resistors, each of the resistance R are connected in parallel, then total resistance is equal to R over N. What does this sentence means? This means, class, that if your R sub 1 is, let's say, 1 ohm, R sub 2 is still 1 ohm, and your R sub 3 is still 1 ohm, which means that your resistances have the same value. Okay? And you connect them in parallel. Okay? Kahit ilang number, kahit ilang n of resistors connected in parallel. Let's say you have 10 resistors connected in parallel and they have the same value. So how are you going to get or to solve for the total resistance in parallel? So you simply do, class, this formula, which means whatever the value of that resistance, just divide it by the number of resistors. Okay, let's say, for example, each resistance is 1 ohms or 1 ohm. Let's say there are 10 resistors here connected in parallel. Say, for example, class, the 10. So what will be the total resistance? So the total resistance will be 1 over 10. Can you follow? So this will be your total resistance. Okay? Again, this is only applicable if your values are the same and if they are connected in parallel. Okay, class. Now, let's talk about the reality, class, or in our real world. In our house or in your house, what is the connection of our light bulbs? Because in your house, class, you don't have, or di ba yung ilaw natin is more than one. Okay? Meron tayong ilaw sa kusina, meron tayo sa kwarto, meron tayo sa sala, meron sa CR, right? Now, what do you think is the connection of those bulbs? Because bulb, class, is a load which represents resistance. Okay? What do you think is the connection there? The connection is parallel. Did you get it right? Again, the connection of our bulbs, light bulbs, are in parallel. Why? Why is it connected in parallel? Recall that in parallel, your voltage supplied is just equal to the voltage supplied or across each resistances. So, if you can observe, class, our bulbs are rated 220 volts or 230 volts, which is, etong 230 volts, yan din yung supply natin, di ba? Which is coming from our panel board or which is coming from the Akelco. So, what will happen if you connect your bulbs in series? We have learned that if we connect components in series, what will happen to the voltage is it will be distributed, or what will happen is there will be voltage drops that will occur. So if you have your 220 and you connect it in series, so yes, your 220 will be distributed, or it is not the same all throughout. Okay? What will happen to your bulb if that happens? Will it light up? Will it light up? Yes, it will light up. But you will observe, class, that the lighting or the illumination of your light bulb is dim. Yes. And what will happen if that connection will continue? Masisira yung light bulbs mo. Oo. Kasi yung kailangan niya dapat supply is 220 eh. So, ba't mo sinuplayan siya ng kulang? Kasi magkukulang yung, class. Kasi, like for example, you have 5 light bulbs connected in series. And then, 220 lang yung supply mo. So, syempre, 220 na yan, magde-divide pa yan sa 5. So, ilan lang yung pupunta sa kada bulbs, di ba? Unlike if you connect your light bulbs in parallel, so whatever supply that you have, it will be just the same in each bulb. Okay? So, that is the reason why. Okay? And class, you can also observe that in a system, for example, when a light bulb, halimbawa yung light bulb nyo sa kusina is may sira. Okay? May sira siya, but you can observe that your light bulb in your room or in your living room or even in the dining room are still working. It's because class of parallel connection. Kasi kahit nasira na yung isang bulb, hindi maaapektuhan yung yung other components mo. Unlike if sa series, pag sira yung isa, maaapektuhan yung lahat. Hindi yan gagana, class. Okay? That's why in our lights, it's very important that it is in parallel. But of course, class, there are other connections na ina-apply naman yung series, of course. Especially pag kailangan na ipababa yung, for example, yung current. Okay? So, that's it. That's it for the series and